Okay. We have a lot to do today. I feel the pressure right now of trying to finish this book, and we have 3 classes left. We're going to do a quick summary of just the formulas from chapter 13 so far, because there is an enormous amount of material. This sheet right here, everything I'm showing you here is online in Canvas under Files. You may print this and you may bring it to the final. Nope, that's not the one. That's just a summary of chapter 13, section 2. This is all of chapter 13. Okay, it is many pages long. All right, so again, I'm going to move fast through this. We started off this chapter, we did line integrals in 2-dimensional space. So you had a curve in 2-dimensional space, and what you were doing was evaluating a scalar function at every point on that curve. I'm trying to do this fast, but you had some curve C, and you're basically picking these points, plugging those points into a function, and adding up all those values. So this gave us like the area of a curtain, all right? It was the area below a surface dropping the curtain down. We also said we could do that with respect, that was with respect to arc length, then we could do it with respect to x or y, all right? Then there was some stuff about changing directions, blah, blah, blah. Then we said, let's extend this idea to a curve that's in 3-dimensional space, all right? So it looks about the same because I'm writing on a flat sheet of paper up here. But now this is in 3-dimensional space. We take these, we plug these points into a scalar function, f of x, y, z, and we add all those up. And that we can't really understand visually, but this was the line integral along the curve C in 3-dimensional space. And then there were 3 additional integrals we could do instead of with respect to this right here. That was like the arc length, all right? We could do it with respect to x, with respect to y, or with respect to z. Okay? Then we introduced the idea of moving a curve C through a vector field and trying to add up what's going on, you know, the effect of moving this through the vector field. Well, you got all these vectors in here. And that was our, what do they call that? The work, right? That was work. And work turned out to be this formula right here, okay? And then, after we did that, we got the fundamental theorem of line integrals that said if that vector field was conservative, then we could just evaluate it at the 2 endpoints, which was part of your take-home test that was on there. And then we got to Green's theorem, which basically gave us a way of computing work. Remember, this is work. And it said this: if we had a curve that was closed, right, like this, then finding the work along this curve was equivalent to doing a double integral over that area. And you'd have to compute these partials, right? That was Green's theorem. And that was also a homework problem, that one that looked like this. Okay? So the fact that it's closed curve, you can tell because of the little circle around the integral sign. All right, then we did some stuff. We talked about curl, we talked about divergence, and then I told you that there were 2 other forms of Green's theorem that we could talk about later. And then we started talking about parametric surfaces, how to draw things using R of UV. Now, I didn't talk too much about this. Here's the way you can draw cylinders. Here's the way we draw spheres. And then here's the general idea of a vector function. If your z component is a function of x and y, then we can rewrite it this way, right? That we did talk about that a little bit at the end of class last time. We talked about tangent planes, gave you a formula for tangent planes, and then we talked about surface area, right? And that's where we are right now. So the surface area of a surface is this formula right here, which is the double integral over d D is the domain of your surface function, and it's the magnitude of the cross product of the partial derivatives with respect to area. That's where we are. Yes? Okay. And now what we do is, one more thing. If this vector function can be written z as a function of x and y, then this formula simplifies to this. And that's an easier thing to compute. That's where we ended last class. So now we talk about surface integrals. Once we get through surface integrals, we do oriented surfaces, then surface integrals over vector fields. So we're going to move our surfaces into vector fields in a little while. Then we're going to get a three-dimensional version of Green's theorem. And then we're going to have finally the divergence theorem, and that'll be the end. So that's where we are. That's where we're headed. 13.9 is divergence theorem. Okay, surface integrals. All right, given a scalar function, so we're still talking about scalar functions. We are not talking about vector fields yet. So we have a scalar function f that is defined on a surface capital S. That surface capital S has a vector equation that is given to us by some surface, r of u v. So r of u v, where u and v are the domain of this draws a surface, right? That surface we're calling S. If we want to evaluate some scalar function at every point along that surface and then add that up, then we get what we call a surface integral. So imagine it this way. We have a three-dimensional surface. All right, this is S. And what we're doing is we're taking every point in here and we're plugging that into some function, and then taking those values and adding them up. That is what a surface integral is. This is different than a line integral, because line integrals, what we do is we take the points along a line, plug them into a function, and add them up, right? So this is like more than this, isn't it? You're doing everything along a surface instead. So to do this, here's the notation for it. Okay? Here's a notation for it. And I want you to pay close attention to this, ds. That is a capital S, not a lowercase s. D little s and D capital S are completely different things. Do y'all remember what D little s means? Arc length. That's with respect to arc length. D capital S means respect to surface area. Okay? Surface area. So if you look at this formula, I've got a couple of colors here, see if I can color code this a little bit. This is the notation for a surface integral. You're going to take the function and evaluate it at all these points, right? But how do you draw these points? What do you use to draw these points? I mean, to draw the surface, what are you using? That, right? R of uv. So this is saying, right there means you're going to evaluate your function along the surface at all the x, y's, and z's within that surface. Do y'all remember if I plug in a value of u and if I plug in a value of v, won't it give me a point, a three-dimensional point? Yeah. So once I know what u and v is, it'll give me a three-dimensional point, an x, a y, and a z, and that I can plug into f. So this is the same as this, right? Okay, that means D capital S is what? This right here? Must be the rest of this, right? And do you recognize this? That's the surface area, isn't it? That's the previous section that we just did. Yeah? In other words, if I were to take this and I were to tell you that my function f of x, y, z is 1, the constant 1 function, then what is this formula? This would be double integral over s of 1 d capital S, right? And what does this represent? The surface area of S, right? This is a common theme that we've had several times now. What was a double integral of 1 double integral over d of 1 dA. Area, that's the area of D. What was the triple integral over E of 1 dV? The volume of E. So we're saying here, the double integral of 1 ds over S is very much like this one. What's the big difference between that one and this one? What's the big difference? This surface is floating around in three-dimensional space, right? Here, our D is flat on a sheet of paper, right? It's fixed on a sheet of paper. We're actually able to find surface areas with both of these formulas, but this one is more general because our surface can actually be moved off the flat sheet of paper. But just like we had before, if we take, instead of having 1 here, if we have a function in there, then it gives us some other value. It has nothing to do with area. I'm just trying to get you to see that this formula is just an extension of what we were just doing, but now we're adding this new component to the front, or new piece to the front of it, all right? Okay, so let's try to work through a problem. All right, find the surface integral over the surface S of xyz ds, where S is the part of the unit sphere above the cone z equals the square root of x squared plus y squared. All right, so can you tell me what is the scalar function that we're going to be integrating? xyz. And that's what we were given, right? xyz. All right, let's try and draw the surface. It's, the surface is part of a sphere, right? Unit sphere. So our surface looks like, it's part of this sphere, isn't it? Radius 1. But it's the part that is above the cone z equals square root of x squared plus y squared. So what does that look like if I draw this? Like, well, if you're unsure, just plug in some points. Right, like plug in 0 for x and 0 for y. What would you get? Z is 0? So the origin is part of that. Can you ever get negative values? No, because z can't be negative because you're taking the square root of a number. Okay, one easy way to do this would be to, let's just see what happens if y was 0. If y is 0, this equation becomes z equals the square root of x squared. Z equals, yeah, the square root of x squared, which is really z equals absolute value of x. And doesn't the absolute value of x look like a v? Same thing would happen if I let x be 0. We get z equals the square root of y squared, which means z equals absolute value of y, which would be another v, right? So it basically looks like v's, but it's a cone. So something like that, right? You all okay with that? Now, when we say it's the part of the sphere, unit sphere, that's above the cone, then you have to understand what we mean by above the cone. If I put my hand inside like this, my hand is above the cone. If I put my hand like this, my hand is below the cone, right? So I want the parts that are part of the sphere that's above the cone, a part of the sphere that's above the cone but still lives on the sphere. So do y'all see where that is? It's a little top piece, right? It's this piece right here, but it's going to be kind of rounded, right? It's like a patch, a little dome, isn't it? Like a little dome, like a little cap, right? You'll see that? It's not solid though, right? It's just the surface. That piece right there is what we're talking about. Take everything else out of there. Okay, yeah, I didn't know what that was called, but yes. Okay, that's our surface that we're integrating over. We need to be able to draw that surface with a parametric function. We need to come up right now with the r of uv. Find r of uv that will draw that. So what would you suggest I use? Spherical coordinates, right? Use that. We drew spheres last class, didn't we? So we could probably use that one again. R of uv, and what was it? It was like, what did I use? I want to stick to what I used last time. Sine, double check it. Because remember, we have the freedom to change u and v, don't we? Didn't I use u as the one between 0 and pi? Okay, I did sine u, cosine v. Okay, sine u, cosine v. The reason I want to use the same one from last time is because I want to use some of the work we did last time. I don't want to have to redo the work. U here was between 0 and pi, and v here was between 0 and 2 pi. Now, that will draw us the whole sphere, right? Do we want the whole sphere?
No.
We don't want the whole sphere. We only want that top piece. So how are you going to determine that top piece? I need to restrict something, don't I? What do I need to restrict to draw this little red piece?
You need to restrict phi to 45 degrees.
So is the V okay?
Yes.
Right? So if I want to draw that, imagine you're standing at the origin. I want to be able to kind of rotate out, right? And then I want to be able to spin around, right? Like spin like this. And that should draw me that little patch up there. And then I need to vary my angle so I draw like a bunch of rings up here. So if I vary my angle like this, I should be able to draw that little piece. That angle for us is u, isn't it? So I don't want it to go from 0 to pi. Now the v is okay because that allows me to spin around. What about the radius? Like how far out I went? It's 1, and that was what this was, right? There was a 1 here, and a 1 here, and a 1 here. So this is good. We just need to figure out what this is. I heard 45 degrees, which we'll want to use pi, in terms of pi. But how do you know it's 45 degrees? The cone is 45. So if we slice this in half, right? Imagine we slice it and we look at a cross section. It would look like this. And then we would go like this, right? And I said that these were like lines off of an absolute value, weren't they? And if it's an absolute value, then let me draw like an x and y axes here, xz axes. Then if you go out 1, up 1, out 1, up 1, this is going to have a slope of 1, which means, yes, this has to be 45 degrees, or pi over 4, right? So we are going to restrict this between 0 and pi over 4.
Is it always going to be pi over 4?
Well, if it's that cone on the unit sphere, yes. But if it was that cone on, or a different cone, like if you change this to like 2x squared plus y squared, then it would be different. And then you would have to do a little bit more geometry to try and recover the angle. All right, questions? We have the vector function that draws the surface, right? And what we need to do is we're trying to do the double integral over s of f, little f, evaluated r of uv, and then what? Absolute value r u sub u cross r sub v d a. Sorry, and this needs to be converted over to d because now everything's in terms of u and v. Now, where am I getting that formula from? The previous slide, right? The previous slide I showed you. right there. Okay, that's what I need to do. Okay, let's see if we can do this. So let's go ahead and start plugging some things we know in to our double integral. Do we know our restrictions, our domain restrictions? Do we know them?
Yes.
Yes, they are these two, right? And they're both constants, so it doesn't matter which order I go in. So I'm going to go, let's go 0 to 2 pi on the outside, and then 0 to pi over 4 on the inside. That forces my order of integration now. Question?
So the first, the 0 to pi over 4,
Uh-huh.
is that integrated, is that getting everything below the zone? Or am I looking at different?
When we did spherical coordinates, remember that was the phi, and phi is always measured from straight up down, not straight out up. Does that clarify it? Yeah, okay. Yeah, so I should have said this. This is 45, but since it's 90, this is 45. Yeah, maybe I should have clarified that. Yeah? We were interested in this angle right here. 0 to 45. All right. What does f evaluated at a vector surface mean? I'm going to plug in, I'm going to replace, here's my function, right? X, Y, Z. I'm going to replace x with what? With whatever the x component is of my surface. So it's sine, this sucks, sine u cosine v, right? Times, now I have to do y. Y is sine u sine v. And then I have to do z, which is cosine u, right? All of that times, now I need the magnitude of the cross product of the partial derivatives, which means you would have to take the partial of this with respect to u, partial of this with respect to v, do the cross product, and take the magnitude. We did that last class. So please refer to your notes. It's a lot of work, right? What did we get? Wasn't it like sine something? Well, that's when we, no.
That's
The-
for our side, yeah.
Magnitude of cross product.
I have it, but
It should just be like sine something. Hold on. Yeah, this is our cross, but where's the magnitude? Here's the magnitude right here. Sine u. That's with the radius of r. We did that formula with radius r. If you look back in your notes, and you'll see that what we got was that the magnitude of the cross product was r squared sine u. But for us, r is 1. So I don't want to go through all this partial and cross again in magnitude. But you can appreciate the work, right? So this is sine u. And then I have what? dA, right? But dA is d what, d what? It's going to be d, the way I ordered it there, u dv, like that. Okay? Now this is the double integral 0 to pi. All right, let's get all of our u stuff together. Here, I've got a sine cubed u, don't I? And what about cosine? I have a cosine u? Right, like that. And then in terms of v, I'll do sine v cosine v. And then I still have du dv. Did I miss anything, or is that everything? Everything accounted for there? Is that okay? Questions?
why did you drop the first integral?
Oh, because I was about to split it and I forgot to put it. That's what happened. I got one step ahead of myself. Thank you. I was going to ask you what we could do here, because this is all u's, right? all your u's are separated from your v's, like your u's and v's aren't mixed together. So you could actually split this into two integrals with what between the two integrals? Multiplication. This is one of those special cases we talked about way in the beginning with double integrals, that I can now make this the integral from 0 to 2 pi, and then that'll be dv times integral from 0 to pi over 4 du. And this one will have just my v stuff in it, which is sine v cosine v. And this one right here will have my u stuff in it. We okay with that? Questions? I think these integrations are pretty straightforward. So let's finish this one out. I think this will finish pretty quick here. All right, what is the antiderivative of this? Well, you could do basic u sub, right? U is sine v, derivative of that is cosine v. So this will be 1/2 sine squared v evaluated 0 to 2 pi times, do I need to do any more work? No. Because if I evaluate sine at 2 pi, what do I get?
0.
And if I evaluate here, this is going to be 0 times this, it's going to be 0, right? Now, just for the sake of doing it, what's the antiderivative of this? 1/4 sine to the 4th u, right? Evaluated 0 to pi over 4. And now, when I plug in pi over 4, I would get something other than 0 here, but it won't matter because I'm multiplying by 0. Okay? Any questions? Because of this, right? That's the main thing.
So the surface area is 0?
Okay, did we just calculate the surface area?
No.
Okay,
So, okay.
you felt like, okay, good. I'm glad you mentioned that. Had this not been here, that would have been surface area, okay? But since it was here, what we were doing is we're moving along. Here's that top patch, right? That S. We were taking points, and what we were doing is we were taking the point, and we were saying multiply the x coordinate times the y coordinate times the z coordinate, right? And then add that to this one, multiply x times y times z, and we did that for every single point. Some of them turned out to be positive, some of them turned out to be negative, and in the end, when you add them all up, we got 0.
Okay.
And it's really based upon the symmetry of the surface along with this very kind of clean formula, the x coordinate times the y coordinate times the z coordinate. Understand? Okay. All right, some applications. So some things you could do with this surface integral is that if you knew the density at every point on that surface, then if you add up all the density points along that surface, it would give you the mass. So that would be this right here. Surface integral over S of the density function with respect to surface area would be your mass. And then you could get x bar, y bar, and z bar. These are like the formulas I gave you for that line problem for the test, right? I gave you those formulas in class? The one for the take-home exam? No? So I did not, right? I didn't give you those formulas. You needed to find those somehow. They were in your book. I was hoping. The thing I was trying to get you to remember, right, is that don't forget that you have a book. Like when you're in a class and you're being presented information, don't forget that the book is still, there. It has information in it. So just because it's not presented does not mean that you forget about the book. All right.
So with like the exam, are you going to have to, or are you going to be able to write like a sheet?
I'm not going to ask you for a mass or center of mass problem for a surface. This is more just like, hey, like this has been a common theme all semester, is that every time we get this new type of integral, we have some applications. So we could do this with it, right? And this is density function. If that was the charge density, you could find like the total net charge on this surface. You know, charge, electrical charge is what I mean by that. It just depends, it all comes down to what does that function mean. Then it gives meaning to the integral.
And the final's not comprehensive.
Comprehensive, I think chapter 13 is going to feel like a comprehensive test. Yes.
So we're just going to get chapter 13 or chapter 13?
There will be more than just chapter 13, but the final is a hard test for me to make because chapter 13, I could give you like 4 separate finals on chapter 13, you know? There's a lot of information in chapter 13. Let's talk about the final later. Let's see how far we get. All right, a special case. So just like we had with the surface area, we ended class last time with a special case where your z is a function of x and y. Then that formula for surface integral, it's going to change. And what's going to change is that magnitude of the cross product now becomes this, right? That was the little shortcut that we get. And then also, our scalar function, instead of evaluating along the vector function r of uv, we're just going to leave x. All our x's are going to be left alone. All our y's are going to be left alone. But our z will be turned into the function that we're given. Now, there are another 2 equivalent forms of this. If you have let me write it down first, and then you can tell me what's going on here. Oh, I forgot the F in front here. Partial, oops, I forgot something here. Let me call this G so that we maintain some consistency here. Okay, so what would this formula be for? If instead of having a surface where the surface is like this and the domain is on the ground in terms of x and y, instead you had a surface which was sideways. Okay, so look, this case right here, you have the domain is on the ground and your surface is up here. Okay, so x and y are your domain on the ground, your surface is up top. That's this case, which is this. Z is a function of x and y. This case, we switch it up. Now your y is a function of x and z. So this would look like this. All right, so y is a function of x and z. So now your domain lives on the xz plane wall, right? And then your surface comes out like this. So it's sideways. Got that? Then we could use this formula. And there's one last one, which would be, what would we change here? This part right here would be g of yz, and then y, and then z. And then what would change here? This would be partial dy squared, and this one dz squared. Understand that would be the third case? And that would be, picture-wise, it would be, your domain is where? On the yz plane, so on this wall, that's d, like that. And then it comes out at us, our surface is like that. Okay? Understand the difference between those? What's the advantage of using these formulas over the previous formula? What's the advantage? What do you not have to do? the partials crossed magnitude, right? You don't have to do the magnitude of those cross product partials, and that part in itself can be time consuming. I skipped that whole step on the previous problem because we spent 15 minutes doing it last class. So that's the advantage of these. Now we're going to have to see this in action. So let's get it rolling here. Aha. There we go. There's a nice looking little surface there. Let's find the double integral, surface integral. Let me call it the right thing here. Let's find the surface integral of the scalar function x with respect to surface area where s is shown below. And I want the surface integral over the entire surface. That means the entire surface. Backside, front side, everything. Why'd that get so big?
You zoomed in.
Did I zoom out?
Well, we have 3 different sublimits.
Will I what?
3 different double integrals.
It looks like we're going to have 3 different surface integrals, right? Oh, there it is. Okay. All right. We're going to have 3 surface integrals. One along this side, this surface, one along the back surface, and then one along the green surface around the edge. All right, let's talk about those surfaces. Let's label them. Let's call one of them S1. Check it out. S1. S2. I know I brought green today. S3. Okay. Which one do you want to go after first? Wait a minute. What the heck? That's missing something. We're missing, you can't see it on there. Is it X?
Yeah.
It was X? Yeah, X, right? There, that should be good. X. Okay? So which one do you want to do first? You want to do S1? Okay. What can you tell me about S1?
X is 0.
X is 0, yes. Anything else you can tell me about that?
It's on the YZ plane.
It's on the YZ plane. Can we tell what the... it's a circle, right? Okay, it's a circle. It looks like this. Here's Y, here's X, here's Z. It's like this backside, right? Like this. It is unit. Now, the reason you can tell it's unit is... There we go. Okay. Because of this right here, right? So we can tell it's a unit circle from that. I just gave you 3 formulas, shortcuts on doing surface integrals. If you can somehow write your surface as a function of x and y, you do it one way. If it's a function of y and z, you do it another way. If it's a function of x and z, you do it another way. So is this surface a function of x and y, like this? Like on the top, ground is x, y. Is it that? No. Is it sideways, where it's x and z, y is a function of x and z? No. Or is it like coming out at us, where you have y and z in its surface, it's a function this way? It's that, right? So this right here, this is, x is some function of y and z. Now, even though there's not a y and a z there, right, it's a very boring function. What is it? 0, right? Y'all okay with that? So according to our previous little note, the surface integral over S of x ds should be equal to the double integral over d of x, right? Now this is our function. Hold on, this is our function. I shouldn't put x here. X is what we're supposed to be evaluating, right? X. And that's going to go into that scalar function, isn't it? So I replace x with what here? 0, because x is 0, isn't it? So this is 0 times square root of 1 plus the partial of g with respect to y, which is plus partial of g with respect to z, which is 0 dA. But none of this matters because this was 0, right? Now just step back, take a breath, and think about this. I'm supposed to pick points along here, right? On that surface, and plug them in to what? That scalar function. My scalar function is the function f of x, y, z equals what? X. Okay, so if I pick a point on here, on this little surface, what's x? 0. So anytime you plug any point in here, you're going to get 0, and then when you add them up, who cares? They're all 0. So we should get 0 as an answer, right? Okay, so we get 0. Nothing more to do. Questions? We're not done. That's just S1. Eric, you got one? What? No? Now, just for the sake of thinking through, if this had not been 0, and we would have had to continue this problem, how would you have proceeded with this problem? Like, let's say this came out to be something. You would be looking at a double integral with respect to area, right?
Yes.
So how would you go about representing the domain of that function, or that surface?
Did you change it to UV?
Change it to something.
Y and Z.
Polar. We would go to polar. This is a polar region. Now we're actually going to have to do that right now. I just wanted to see if you could start thinking about this ahead of time. Let's go after S2. All right. Over S1 we got nothing. S2. Tell me about S2. Well, we know x is equal to 1 minus z, right? So x is, well, no, because we're on S2, x is not 0, right? So could you say that x is now a function of y and z? Yes, right? Now, it only has z in it, but it still is a function of y and z. So we can use that same exact little shortcut, can't we? Double integral over S2. Did I put S1 on the last one? I don't think I did I?
No.
Please change that to S1. Of x ds is equal to double integral over d. And now what we're going to do is we're going to take our scalar function, right, here. This is our scalar function x. And we're going to plug in whatever x is into this. So what is x? 1 minus z. So that's this piece, right? And then what does the ds part become? Square root 1 plus partial of g with respect to y squared, so 0, plus partial of g with respect to z, which is negative 1, and then squared, and then dA. You following me? So we got a root 2 there, right? That root 2 can just come out of everything. It's a constant. Root 2, double integral over d of 1 minus z dA. And what is this? I need to somehow look at my d. My d is my domain for my surface. Now, this was our surface, right? This was it's the blue one right there. So that surface was a function of y and z. So if we project that surface onto the yz plane, what does it look like? So if I take that, I'm going to kind of exaggerate this here. So we would get the unit circle, right? And then we have our surface comes out like that, right? So it's kind of like this is our surface, but if you project that onto the yz plane, you get the domain of that surface on the yz plane, which is a circle radius 1. Yes? So how could you turn it? Yeah, so how would we do that if we do polar here? Now be extremely careful, because our circle is on the yz plane, right? So I'm going to go to polar. And to go to polar means I'm going to replace, normally we do x with r cosine theta, right? And we do y with r sine theta, right? But that's if we have x and y as our plane. Here it's yz. So we're going to let y be equal to r cosine theta and z be equal to r sine theta. And then we have the identities y squared plus z squared equals r squared and all that stuff. What I'm trying to get you to see is that because our function is a function of y and z, our switch to polar has to be in terms of y and z, not x and y. Okay? Because we're going to have to replace that z, aren't we?
Yes.
What are you going to replace it with?
R sine.
R sine theta. The only way you know that is if you understand that the polar conversion was in terms of y and z, not x and y. All right? Okay, what are the restrictions on r and theta going to be?
0 and 1.
So r will be 0 to 1, and theta will be
0 to 2.
0 to 2 pi. So we are going to draw the unit circle, but it's just the unit circle on a different plane. All right, let's do the switch. If we do the switch, we're going to get equals root 2. Now we can go 0 to 1, 0 to 2 pi. Oh, I did that in a different order I normally do it, didn't I? I usually go 0 to 2 pi and then 0 to 1. Let's do it back. Okay. And then I'm going to have what inside here? 1 minus r sine theta, and then r, because we did polar, dr d theta. And does that look like something you could integrate? Do that with respect to r, do that then with respect to theta, and grind out the answer. So I'll leave that to you. Is that okay with you? Equals dot, dot, dot. So whatever we get there, that answer, we're going to put it on hold, and now we've got to go get S3. Questions? How do y'all feel so far? Is it starting to feel like the glass is overfilling onto the table yet? No? Like, that's an analogy, like information overload yet? No? Tell me about S3. Okay, so S3, we've been lucky. S1 and S2, we've been able to use shortcuts because we could look at them both as functions of two variables. But can you do S3 as a function? It either needs to be that z is a function of x and y, or y is a function of x and z, or x is a function of y and z. What do you think? X is a function. We're talking about the green one, right?
Yes.
You could do either y as a function of x and z, or z as a function of y and z.
How can you get that x is a function of y and z? I don't quite see that. See, here's the way I think about it. This may help you, it may not. Okay, here's x, here's y, here's z. Let's do it this way. Let's use the room again. X that way, y this way, z that way, right? So if you have a surface that's like this, this is a function of this stuff is coming from down here, getting plugged in, and you're getting this surface, right? So this is a function of x and y, right? Now, if your surface is like this, then the domain is over there, right? What's over there? X, z, right? Those points get plugged in like this. If your surface is like this, then your points are coming from over here. So it's the y, z. Understand? Function of x, y, function of x, z, function of y, z. You with that? So what about this? This is this weird shape. It goes like this. Kind of comes out to a point, goes back in. I don't know. I can't really draw this very well. I don't know. What the hell is that?
The slide.
It looks almost like, yeah, that could be a lot of things. My daughter would love to see that. She could see 20 different things in that. I'm trying to draw this green thing, man. It's supposed to be like this part, but see, it wraps around back the other side, right? And it's on the bottom too. So is that, could you look at it as a function of x and y? Like, is it a surface like this? No, because it curls back on itself, right? So it would be kind of like me going like this. That can't be a function of x and y because you're going to have like a failed vertical line test almost. But then it's going to fail this way also. And then this way, it's just a circle. You're not going to get the whole surface, which means no shortcuts. We have to draw the surface with an R of uv, and we're going to have to cross it, and we're going to have to take the magnitude, and all that shit's going to happen. Okay? You know what I'm saying? I don't think I said shit.
I think you did.
I don't think I did.
You just said it now.
But I was only clarifying. I was just clarifying.
So does that mean bonus points on the final?
No, they offset each other. Okay, so S3. All right. So we did this handout, right, where we went through example A, B, C, D, E, F, all those, and the whole thing was to try and get us ready for something like this. Okay? All right. You need to draw me that green surface. What do all those points on that green surface have in common? They all lie on a circle, don't they? They all lie on a circle. And that circle is basically equivalent to a circle that would be in the YZ plane. So that means that my Y and my Z have to be able to draw the circle. So what should I put here for Y and Z? So we usually do cosine. Your choice. U, okay. Sine, U. All right. Every point that I draw now is going to lie on a cylinder that is on this, right, this unit cylinder. I just need to control the x coordinate now. And how do I want to control that x? I still have one variable to mess with. I need that v, my x coordinate, to be between 0, which is the backside, and 1 minus z, which is the plane equation. So what do I put here? V. U is going to be between 0 and 2 pi, and V is between 0 and 1 minus z, but z is sine u. So imagine we had not done that handout, right? And I just come in here and I start saying, all right, well, that surface is obviously going to be, draw the circle, there's V, control V. You see, I think that would be a little bit more difficult for me to just throw out here on top of all of the other stuff that's happening. It's still kind of, yes, exactly. All right, we must proceed. What do I need now? Maybe we'll get lucky. What happens if we take the scalar function here and we plug in the x, right? Because that's what I'm going to do. Do we get lucky or something? No, it just turns into v. So it doesn't like go to, it'd be great if that was 0 or something, right? Or 1, but we're going to have to work it.
So now do you have to take the partial?
I need to take the partials, and I need to cross them, and then take the magnitude. And let's just hope for the best, all right? And I think I'm going to take the picture out of here so I can work on that side of the board. Okay, partial of r with respect to u is a vector. The vector is 0. Feel free to sing along. Negative sine u, cosine u. Okay, good. And then partial of r with respect to v, which would be 1, 0. Ooh, I like to see all these zeros because I'm about to cross it. Okay, the cross product. Hey, and just for your own information, you know how we did the shortcut on the previous two surfaces? You could have done this with the previous two surfaces. You just would have worked a little bit longer, that's all. All right, cross product. So I want the I component, so I cover these up. 0, nice. It's a vector. Cross product's a vector. Cover this up for the J component.
Cosine u.
Cosine u, and it'll be positive, right? It's not going to matter because when I take the magnitude, I'm going to square it anyway. So even if I screwed that sign up, I'd be safe. Here,
Sine u.
positive sine u. Oh, and when I square those and add those together, I'm going to get a Pythagorean identity. It's going to be 1. It's going to be nice. Okay. Magnitude is square root of 0 squared plus cosine u squared plus sine u squared, which equals 1. Yes. All that for 1, right? Okay. Ready for the answer? Or for the integral now? Our integral now turns into the double integral over d of f evaluated on our surface, which we already said was what? Just the x, which was just v, times the square root of all that junk, which was 1, then dA. Now tell me about your region D.
You have those two parameters.
Your region D, right, which is the domain that drew this surface. You don't need to look at any shadows or projections. It's right here. This is your restriction. So we can go straight from this over to double integral. Now the order absolutely matters here, right? Because this is not a constant. So the outer integral must be from 0 to 2 pi. The inner integral must go from 0 to 1 minus sine u. Now the good news, I'm only integrating v, and I'm going d v du. Let's take it all the way, right? No? Yeah? No? We'll take it all the way. Well, wait, no, because on S2 I didn't take it all the way, did I? So we're not going to be able to get an answer anyway. And I think this is doable. First antiderivative, 1/2 v squared. Then you have to plug that in, and then 0. And then figure that out. Then integrate again. You're going to have sine squared in there. So, you know, it's life. It's the reality of where you are in your life right now, okay? This is what you have to do, I guess. Yes?
Would a big rule of thumb be like if the boundaries, if there's a variable in there, it's going to be integrated first?
It's not a rule of, well, I guess it is a rule of thumb. You have to do it. It's not optional. If you have one of your variables is restricted between two constants and the other one is somehow a function of that variable, that has to be the inner integral. Has to be. All right? No switching. You can only switch when they're both bounded between constants. And that's because when you're bounded between two constants, you're integrating over a rectangle. So it doesn't matter, you know, if you integrate over a rectangle, it doesn't matter if you go up, 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 up this way to add up all the areas, or you go over. It doesn't matter which way you go.